Today, I'm here to talk to you about a new discovery I've recently made in quantum mechanics, generalizing Heisenberg's uncertainty principle. Now, to remind you what that is, back in 1927, Heisenberg noticed that for certain pairs of observables, such as position and momentum, which is just mass times velocity, that it's impossible to know both of them perfectly at the same time. So for instance, if we make a highly precise measurement of a particle's position, then we're going to be very uncertain about its velocity. This is because deep down on a fundamental level, everything is made of waves, and that determines what's measurable and exactly how it's measurable and leads to this effect. What I've discovered is that it's not just between two observables, but between any number of them, no matter how many we're talking about. So let's take a look and see how all this works. Welcome to today's talk, New Quantum Multi-Operator Heisenberg Uncertainty Relations, based on this paper that I wrote, and you can find a link for that in the description box. So let's start by talking about Heisenberg's uncertainty principle. First, consider a pure wave going from negative infinity to positive infinity, and it has a definite wavelength lambda, which is the distance between two consecutive troughs or peaks. And the question is, where is it? We're uncertain about the position. In fact, we're so uncertain that we say our approximate uncertainty in x is infinity, okay? Because we really just don't know where this thing is. It's like kind of everywhere. And then because of that, we say that momentum p relates to lambda by something known as de Broglie's wavelength relation. Okay, this is a famous quantum mechanical equation, and it relates momentum p to the wavelength by this proportionality constant called Planck's constant, which is another famous constant. Okay, if we know the wavelength perfectly and we know this constant, then the whole right side is known. That means p is known, the momentum is known. So that means we have no uncertainty in the momentum if we have no uncertainty in the wavelength. All right, but waves obey superposition, so we can add many of them together, right? So many different frequencies, many different amplitudes. If we add just the right combination up, we can get this localization effect where it goes to zero everywhere except one little local area. And this is basically the simple idea of what a particle is. Now we know approximately where it is, so our uncertainty in x goes to zero. Okay, so we can actually say, once it gets sharp enough, small enough, our uncertainty is approaching zero. And unfortunately then, because that takes an infinite number of frequencies, each with their own wavelength, so each has their own momentum, then that means our uncertainty in the momentum will be infinite when we have this particle-like situation here. Okay, so what he showed is that if our uncertainty in the position is approximately the wavelength, then because of this de Broglie's relationship, we can put the uncertainty in p there and the uncertainty in position there because we're relating it to the wavelength. And then we can multiply both sides by that uncertainty in position, delta x, and we get the product of their uncertainties is approximately h, okay, that Planck's constant. So that's 1927. Then the idea was refined. So quickly it became known that this thing on the right side needs a little bit of refinement. So it's this different quantity h bar over 2. Okay, it's just another constant. And now we know that it's a greater than or equal to symbol there. And instead of approximate uncertainties, we're going to use standard deviation, which is a little bit more refined mathematical way of describing uncertainty. Okay, so that's just the value of the operator minus its own average or mean. Then you square that thing is called the deviation, and then you take the mean of that, and then you take the square root. That's the standard deviation. Okay, then Robertson came along and he modified it a little bit, and he said, okay, well, instead of just a position and momentum in that same direction, we can also have any two observables. Well, not any two, but maybe a general two that are special. And those two, okay, if they do not commute, meaning a times b does not equal b times a, then there's a number here, okay, that isn't zero. So we call this thing the commutator, ab minus ba. If those are the same, it'll be zero. But in quantum mechanics, normally these are matrices and these are not the same thing. So whenever these don't commute, we'll get a limit here that is greater than zero. And that's when we start to get some interesting effects, okay? Then Schrodinger came along and he generalize this even further, and instead of just having a commutator over here, he has what's called the covariance of A and B. So that's just the product of the deviations of both of them, and then you take the mean value. To understand the above results, we have to start with the Cauchy-Schwarz inequality, which is this equation right here. Now, these bold letters, A and B, are vectors, and those are just basically arrows that we label A and B, okay? And then the magnitude we represent with the bars on either side, just like an absolute value, okay? So the product of these two vector magnitudes is always going to be greater than or equal to the absolute value of something we call their dot product, okay, which is sort of the amount of one in the other. This dot product is defined as the magnitude of one times the magnitude of the other times the cosine of the angle between them, right? So if we have two vectors, A and B, and the angle between them is theta, then we're going to take their lengths, multiply them together, and then multiply it by the cosine of that angle theta. Okay, and A cosine theta is the amount of A in the direction of B, okay? So recalling that cosine only goes between -1 and +1. In general, it's less than or equal to 1. If we look at the magnitude of cosine, it's never going to be greater than 1. Okay, so what this means is if we look at the absolute value of the right side of the dot product here, okay, that means that because the absolute value of cosine can never get over 1, then the greatest value that the right side will ever reach in the absolute value is when it is equal to 1. So it's A magnitude, B magnitude is the largest value of the right side here, right? So that means that that's always greater than the absolute value of their product times cosine, because this will usually make it smaller, okay? Now, because everything in this big absolute value on the right side is the definition of the dot product, we can plug that right in on the right side, okay? And what we get back is the Cauchy-Schwarz inequality. So that's a really quick way to derive that. So now let's relate that to the quantum uncertainties. Okay, so Robert and Schrodinger, they wrote things in terms of covariance, okay? Or really that was Schrodinger. But Robertson used a similar trick to this, okay? So for Hermitian operators, okay, that just means we can observe them. That means their mean value is a real number. The product of the deviations, we take the mean of it, that gives us the covariance, okay? Schrodinger really wrote this as a dot product of quantum states. All right, so we start with a quantum state, which is basically just a vector, right? It's a complex valued vector. So we call this the ket of psi, or, you know, the quantum state psi. And they immediately define two new states, all right? So there's psi sub A, okay, that's just the deviation of the variable A times the original state, and psi sub B is the deviation for B times this state, okay? And A and B are observable quantities, all right? So then the idea is to take their dot product, which we call in quantum mechanics an overlap, and we write it like this, okay? And that causes us to write it like this, okay? We're using Dirac notation, and normally we can omit the state even though it's really there. We just sort of don't have to write it all the time. And that gives us the same notation as the covariance, okay? So you can see this is sort of a way to get quantum states to give us a covariance through a dot product, okay? Through an overlap of the quantum states. All right, and if you're not following this, don't worry, okay, I'm just sort of giving you an overview here. Then they used the Cauchy-Schwarz inequality. Because they have this overlap, which is essentially a dot product of quantum states, we can go up and use this dot product relationship here. So there's that quantum dot product on the right, okay, in absolute values, and then on the left, this is what the magnitude of those two states are. And of course, these are not necessarily normalized. Once we put an operator in front of them, they don't necessarily have a length of 1, okay? So these are non-trivial lengths here, okay? And we can then plug in, we know that psi sub A equals this thing, so we can plug that in. We can flip it around, okay, to get the bra version, which is this thing over here, okay? And we notice here, what we have is, we've got like a square of something. We have this B minus B mean, okay, and then another B minus B mean, so this is going to give us a square of this thing. Okay, so we've got means of squares of deviations in here under square roots. We remember these things are the standard deviation for each one of these, whereas the overlap we already showed up here with the covariance, all right? So this is Schrodinger's derivation of this more general result, and it's beautiful, right? It relates this whole idea that Heisenberg had to already well-defined statistical quantities. Now, because we've just seen the importance of the Cauchy-Schwarz inequalities, I knew that if I wanted to make a generalization of Heisenberg's relation, I needed to first derive new Cauchy-Schwarz inequalities for multiple vectors. So we're going to start with just the good old Cauchy-Schwarz for two vectors. Okay, we know that. If I had three vectors, A, B, and C, I could look at each possible pair, A and B, A and C, and B and C. Now for the dot product, order doesn't matter, so I don't need to worry about like C times B or something. So we get just three different relations. Now what I can do is, because these are all true and their inequalities are all in the same direction, I can multiply them together. Okay, so multiplying all the left sides together and all the right sides together, we notice that we've got two A's, we've got two B's, we've got two C's. So that's going to give us the squared of the magnitudes on the left, and then I can just take the square root of both sides, and I get my first new relationship, okay, my first generalization of Cauchy-Schwarz here. So this is the product of three vector magnitudes greater than or equal to the square root of the product of the dot products of all possible pairs, okay? Now let's try it for four vectors. All right, for four vectors, there are 6 possible ways to choose 2. Okay, so it gets a little bit more complicated. And then each vector's magnitude is going to appear 3 times. So when we write it all out and multiply them all together, again, just starting from the original Cauchy-Schwarz, we're going to get 3 A's, 3 B's, 3 C's, and 3 D's, okay, and we got 6 overlaps, right, because there's 6 different ways to pair things out of 4, okay? Then we can take the cube root of both sides, and we get our next generalization, okay? And even though it looks a little bit complicated, it's still quite simple, right? It's still pretty predictable. So I wrote the generalization for m different vectors, okay, and this is what it looks like. And this lets you automatically get this kind of relationship no matter how many vectors you're talking about, okay? And the proof is in the paper. Now this is very, very simple, okay? And there's lots of other ways that people have generalized this, but what you will find is that people a lot of time talk about trying to make the tightest possible inequality. That's actually not important because we can always calculate the product exactly. So we can say the product itself is the tightest inequality. We get an equality in that case. We can always calculate that. So for an inequality, what we're really looking for is simplicity, right? And this is about as simple as you're going to get for a multi-vector Cauchy-Schwarz inequality. I also took subsets of these same relationships, and I was able to get relations like this, where I would only multiply, say, 2 out of the 3 overlaps for the 3-vector case, and then you would get like an imbalance, right? You'd have square of A magnitude, but no square on B and C, and then it wouldn't make sense to take the square root. So in that case, I just made another generalization for it, and that's also in the paper. This could also be useful. It could also give us another perspective, and it's worth looking into. Then, after deriving those multi-vector Cauchy-Schwarz inequalities, I used Schrodinger's trick to generalize them to the quantum case the exact same way, okay? And doing this, I got almost the exact same equation, right? So instead of magnitudes of vectors, we get standard deviations of the operator, right, or of the observable. And so this is the same kind of effect that Schrodinger got. It's just now there's m of them instead of just 2. And over here on the right, we've got a product of many more different covariances between them, but it's the same exact idea, same transformation Schrodinger used. And let's look at a 1-qubit example for 4 different operators, okay? So we have a product of 4 standard deviations, okay, of those 4 different operators, and these 2 parameters are varying over all possible pure states, and of course we can only use a finite set, but we're basically exploring the whole system of pure states for these particular arbitrary 4 operators. And notice that the product of standard deviations creates a surface which is always greater than or equal to this other surface, which is what we see down here in the bottom, okay? And those are the different overlaps, right? But the overlap magnitudes are equal to covariances after we use Schrödinger's trick here, right? So then we've got the cube root of it. This is exactly what this formula says. And notice this is always less than or equal to that upper surface, okay? Now, I've proven this explicitly, but I also tested it for millions of examples, and it worked every time, okay, just like the proof said it would. This is the quantum version of this 4-vector Cauchy-Schwarz generalization that I showed you earlier. Okay, it's the same idea. Now, the unbalanced one that I also showed you, okay, it generalizes very similarly, okay? It just looks a little bit different, but it's the same exact transformation Schrödinger used. And for a 2-qubit example, using 3 arbitrary operators, we get the same sort of idea, right? This strange product on the left, okay, it's an imbalanced powers product, but a computable product nonetheless, is always greater than or equal to the thing on the right, which is the surface down here, okay? And again, we've varied parameters that are important to that state family to explore the whole family, okay? And again, I've got a proof that this works every time, and millions of numerical checks verify that it indeed does work every time. Okay, and this is the quantum version of this relationship that I showed you briefly earlier. Okay, now I also in the paper show how to give results for non-Hermitian operators and unnormalized states, just in case people need to use something a bit abnormal in whatever research they happen to be doing. But then I realized that there's another way that we could generalize things. So the new idea I had, I call multivariance, and I started with the covariance, right? So we can always take the product of 2 deviations of 2 observable quantities, A and B, and take the mean value and call that the covariance. This suggests for 3 operators or 3 observables, we could take the product of 3 different deviations and again take the mean of that and call that the multivariance. So for m different operators, we get a product of m deviations. Okay, we take the mean of that, and that's the multivariance. The paper also defines something called symmetric multivariance because there's lots of different ways to write this product. We don't just have to do this order. So I found a way to generalize that, but it's actually easier to look at this non-symmetric version first. Okay, but even with this, there are multiple different ways to treat it as a dot product, and remember that was the key to Schrödinger's trick. So if we look at just the 3 operator multivariance, notice that there are different ways we could group it, because remember Schrödinger took these deviations, which we're calling the deltas here, and he grouped them with the original state psi. Okay, now I could group all 3 of them with psi and have a very imbalanced thing. So I could have psi 1, 2, 3 be the product of all 3 deviations, right? And that would equal that overlap. But I could also just take these 2 deviations, group it with psi, and have this other one and group it with that. Notice because there's 3, I can't really evenly partition them unless I want to take, the square root of a matrix or something, which is possible, but it's starting to get, there's an infinite number of ways of doing that at that point. So there's no real simple way to do this. So we've just got multiple different ways to do it. Okay, now from this we can get multivariance uncertainty relations because now I'm using overlaps to describe the multivariance. All right, so we can use something very similar. We can actually use the Cauchy-Schwarz inequality, even though this idea is different than that. All right, so using just the original 2-vector Cauchy-Schwarz inequality now, we get the multivariance appearing on the right side, okay, because that's just by definition. And then on the left side, we get various different overlaps, okay, which we can look at in terms of the multivariance again with some kind of square root. Okay, so we can just sort of write it, and normally there's a strange pattern that appears in there, right? So we're going to get a little bit of a strange looking thing over here, but it's really just these overlaps described by using the multivariance definition itself, okay? So this gives us lots of different Cauchy-Schwarz inequalities, which is more than the original, okay? And if we just looked at 2 operators, we would get the Schrödinger relation, but we'd also get 2 additional relations as well, and the paper shows that. So we look at an example for 4 Hermitian operators, okay? And I think just for 1 qubit to keep it simple, what we will get is this product of specific multivariances with a particular order, okay, that's what's showing up here on the left. It's really just one of these specialized types of overlaps. And on the right side is the multivariance magnitude, okay? And so again, we get this surface is always going to be greater than or equal to this surface, and that's proven in the math, but it's also shown through countless examples to always work. So this is another way we could generalize Heisenberg's idea to still get something useful and interesting. Okay, and this is the generalization for the most general case. Okay, it's a little bit more abstract looking, granted, but it's very surprising that it's this easy, and because it's this simple, that's what let me really symmetrize it and make it something much more general than that. Now we have the last major idea of the paper, which is multi-operator squeezing, which is really an application of all the above ideas. Okay, so given a choice of uncertainty relation, such as the Robertson relation, which is just this one here. Remember, we had that commutator from before, and I've squared the whole thing. When we square the standard deviation, we call it the variance. Okay, so this is sort of the standard way of talking about this in this context. Notice we still have this less than or this greater than or equal to symbol here and this lower bound. One of these or either of these can actually get lower than this lower bound, but the other one has to grow to compensate, right? So A could get smaller than this thing, but B would have to get much bigger. And it's typically, we take the square root of this thing to sort of make it so that if they were both equal to the square root, we would get this back exactly. We call that saturation. But now you can either get lower than that equals version, and the other one will have to get bigger, or the other one can get lower and the other one will get bigger. Okay, so that's called squeezing. All right. Now, if we have M operators, okay, I can use my generalizations now, but the consequence of having multiple of them means that subsets of multiple operators can be squeezed simultaneously. So it's not just one at a time, although that is one case of it, but it can be like two at a time as long as the third one grows, okay? So we start with our general balanced uncertainty relation, okay? So we've got like a product of them, and these little twiddles over the top, that's the ones that I allowed for non-Hermitian things, right? So that's more general, but it's the same idea, okay? And the lower limit, I'm just going to call beta, okay? And I've squared everything here. So the beta now is still like a product of covariance magnitudes, but now it's squared the whole thing from before, right? Because we were just talking about variances of things, okay? So this, again, is for generality. Don't worry about that. So for any subset of the operators, any subset of Q of them, we will define something called Q over M squeezing as each one of these variances being able to go below the mth root of that beta parameter, but they're all doing it at the same time. So instead of an or, it's an and here, okay? And that's because the or goes between this and all other possible combinations, right? So in this case, this is like one combination, and this is like the only other combination. Here is just one big combination, and because there's multiple things that can do it at the same time, we have to have the and then the or goes between this and some other combination, a particular subset of variables whose variances goes below that limit, okay? And all of this must happen such that all other uncertainty relations, such as the original Heisenberg for each pair, is still obeyed, okay? So for an example, for three variables, if we have a constant beta, it may look something like this. Okay, this is just a schematic. But you can say that, all right, well, if we have just one variable, okay, we can go back to what we're familiar with. Just one variance goes below this limit, okay? Well, if it's just one of them going below that limit, that would be like this big square slab here on the bottom, this big slab. So that's when this surface is inside this big slab, okay? We can call that 1/3 squeezing, okay? So it's only one operator is squeezed down here, okay? This will be the operator C. That variance is squeezed way down there, but the other two will grow such that their product maintains all of the necessary uncertainty relations, okay? Including the three operator uncertainty relation. Then we have two-thirds squeezing. That's when you got these little tiny thin sort of prisms. So see this little box down here? This sort of makes this little tiny like prism down here, this rectangular prism. Inside of that, okay, we've got squeezing along the B direction, we've got squeezing along the C direction, okay, but it is not squeezing along this A direction here, okay? So this thing can get as big as it needs to in the A direction. The A variance can get as big as it needs to, but that's the only thing that's going to compensate for having two things simultaneously squeezed, okay? So this is what multi-operator squeezing is, and obviously there's multiple combinations of what's possible. So the paper really goes into all of that and shows you all the possible combinations for the three operators and what it might look like. Okay, so one-third squeezing means only one of the three variances is below that threshold, and two-thirds squeezing means that two of the three variances is below the threshold. Now, all three of them can't simultaneously be below the threshold. So this little cube here is like a cube of impossibility. All right, so all of this really is starting to look like the two-operator version, and it's a very, very natural extension of the whole idea. So to sum up what we've done, we found multiple ways to generalize the Cauchy-Schwarz inequalities, okay, such as we had the balanced one, we had the imbalanced one. All of them are extremely simple, but simple doesn't mean wrong, okay? Sometimes that means more useful. And the most important thing is that they let us generalize Robertson's and Schrodinger's overlap method to multiple observables, and that's what really gave us the quantum version quite easily, okay? And the quantum version really retained all the simplicity of the mathematical version. Then I went a slightly different direction with this idea called multivariance, and it's a natural extension of the covariance as the mean of a product of deviations. And it's also compatible with the Robertson-Schrodinger overlap method, but the only weird thing is that it yields multiple different overlaps for a given relation. Okay, so we get like a whole sheafs of different relations, but we can kind of mitigate that by symmetrizing it. Again, the paper shows how to do that. The only catch is it becomes a much more involved calculation to do the symmetrized version of it, even though you then don't have to choose which overlap method that you find most useful. But that one uses the original Cauchy-Schwarz inequality. We don't need the multivector Cauchy-Schwarz inequalities for that one. And it does give us completely different quantum uncertainty relations. So it's nice because we're always looking for different perspectives just to sort of round out our understanding in any different area. Then we took it a whole different direction and applied all of this to multi-operator squeezing. All right, this is a natural generalization of the two-operator squeezing. Anyone familiar with this knows that if you just look at the cross-section here on the side, this is exactly the sort of standard diagram we look at for two-operator squeezing. We've just sort of stretched it into another dimension, and of course it keeps going for a higher number of operators, right? It's just harder to draw in that case. This does lead to some side constraints, but the paper shows exactly how to handle those. And more interestingly, it implies the existence of multi-operator coherent states and multi-operator squeeze states, okay? These are all really good research topics for the future and including technological applications. So anyone familiar also knows the state of a laser beam, for instance, is a coherent state, okay? So that has so many applications. If we find these new type of coherent states, it's hard to imagine that they wouldn't also have lots of interesting applications. And then squeezing, we already have applications for that for improving measurement precision, okay? Using these exotic quantum states can give us some new capabilities that we wouldn't normally have. So it's also kind of likely that we would get something very similar for multi-operator squeezing. And that's it, folks. Thank you so much. I really appreciate it. I hope you found this interesting.